Shining a light onto a panel and it turning on a light seems like trying to plug your phone into a rock and expecting it to charge. However, when you take a closer look behind the chemistry, engineering, and sciences behind them, you'll see why this isn't that far of a stretch. These cells seem common on calculators, yard decor, and public charging stations, but many people don't actually know what happens between the light source entering the cell and the secondary object being powered. In order for large-scale systems to operate on solar power, a solar system is needed. This includes the batteries, inverters, and wiring, and a solar array, which is a collection of solar panels. If you zoom in even further on the solar array, you will see that a single solar panel is made up of a number of different components, including the photovoltaic cells. These cells are the key components to a functioning solar system. This is an enlarged version of a photovoltaic cell, with the actual wafers being thinner than a strand of hair. As you can see, these cells are made up of a semiconductor called silicon. However, in order to make the cells functional, the silicon has to undergo a process called doping. Doping is the process of the controlled introduction of tiny amounts of impurities into a pure material. This is achieved by using thermal diffusion. Silicon is heated to extremely high temperatures inside of a sealed chamber. It is then introduced to either boron or phosphorus gas, depending on the type of doped silicon you're trying to make. This is what raw silicon looks like. It has 4 valence electrons and forms a strong covalent bond with itself. When it is doped with phosphorus, which has 5 valence electrons, 1 electron is left out. Similarly, when silicon is doped with boron, which only has 3 valence electrons, a hole is formed. Now that the silicon is doped, it can be put together to form our cell. However, once the two sides are put together, they form a depletion region. This happens when the extra electrons from the phosphorus doped side fills the holes left in the boron doped side, forming an equilibrium. This neutral zone prevents either charge from passing through to reach each other. This is when light energy actually comes into play. Photons come flying in and travel through all 3 regions. When it crosses through the depletion layer, where the atoms are stably bonded together, it knocks electrons and holes free. The electrons travel up into the positively n-doped layer, and the holes travel down into the p-doped layer. Now, the electrons and the holes want to attract each other just like magnets want to attract each other. So, when the electrons come up, they travel into the fingers all the way to the bus bar, and the holes travel down. Now, you connect the 2 contact sheets together with a wire that forms a circuit, and electrons will travel through, creating a current. Now, if you connect anything through the wire, that electrons will go through and power that thing to go to the hole. So, next time you use a solar powered device, you can actually appreciate how much work goes into making it.